Thanks everyone for coming. I'm Daniel Silva and I'm working both at Goddard and as a PhD student with the University of Colorado Boulder. We're going to be talking about some methods we've put together for predicting the solar wind foot point, which is the origin point of a stream at the sun, using the established Wang-Shili WSA model and adapt for predicting solar wind using magnetogram observations. To start, a little review. WSA is a model that solves for the solar wind velocity and magnetic field throughout the inner solar system, from just above the source surface and down to the sun. It's driven by a magnetogram input and solves equations to fill in the flow field and the magnetic field. So in this talk, we're going to focus on using these flow fields and magnetic field solutions to associate a stream arriving at a location like Parker Solar Probe or Earth with its foot point on the sun. And we define the foot point as the beginning point of a streamline coming out of the sun and arriving at the point in question. There are several reasons this information is useful for research in space weather. When solar wind is measured in situ, for example at PSP or at Earth, we compare the in situ observation with multispectral imagery and learn from that perspective. We can also look at how the foot point region is aligned with different types of solar wind and in reference to its parent coronal hole. So let's start by discussing, in regards to our echo algorithm, how do we find a foot point associated with another point in the solar system? The one-line basic approach is that we map outwards from the model's outer boundary, which happens at 5 solar radii, out to the satellite using a little simulation of the Parker spiral. The more detailed explanation is that we collect the sub-satellite points on the outer boundary over an entire Carrington rotation. This forms a ring of sub-satellite points around the sun. And then for each one of these sub-satellite points, we simulate a parcel moving outwards at the solar wind velocity provided by the model. And we have a little constraint in our Parker spiral simulation that fast streams may not overpass slow streams. But when we move these parcels outwards, if a parcel intersects a neighborhood of the satellite where we know it's going to be based on its ephemeris, we record the trace from the parcel's outer boundary to the corona, and then from the outer boundary to the satellite as the full path of the connection. So in the top right, you can see the fields generated by WSA. The blue line is the outer boundary of the model. The red line is an internal boundary between two different methods of solving the fields. And we see that the field and the velocity is going to be largely radial outside the source, the outer boundary of the model. What our method does on top of just solving individual foot point estimations is that it does this over a large range of model variations and then provides the results of foot point locations in a distribution represented from the model runs. So we know that there's a number of theoretical uncertainties in the calculations. There's the far side of the sun that's unviewable. The model is doing simplified physics. There's a limited grid cell resolution to describe all the phenomena. And so we want to use multiple model runs to capture as much of this uncertainty as we can. I'm going to highlight one particular varied dimension here, which is through the ADAPT flux transport model, which is a data assimilation system. It uses GONG or HMI inputs at the near side and assimilates the far side of the sun. It provides 12 realizations, which is basically 12 different guesses or variations of the model, which represent 12 different magnetograms that we use to produce our solutions. Each one of the 12 realizations is calculated in ADAPT using slightly different parameterization, basically convection cell parameters that affect the flux transport. So without further ado, this is the product that we have created and that we plan to release to the public at CCMC in the next few months. So over this map of the sun, in the green are the coronal holes identified by the different model runs and model variations. In green, they become more transparent when there's less consensus that the coronal hole exists at that pixel. And then in yellow and red is our probability distribution of where the foot point is. And we see that in the bottom, there's a 90% consensus that it's coming from this region and a 10% consensus that it's coming from this region. The way that you might look at this is that the model runs bifurcated in their estimation of the source region, where 90% of the model runs believed it came from this source region, and then the 10% believed it came from this other region. And we draw these blue contours around each one of the regions and sum up the probability in there to give them more of a palatable and easy to interpret analysis of the probability distribution. We can also look at these results in terms of animations over time to see how the footpoint location is moving throughout time. So we're going through about 4 hours every second about here. So we see that it's gradually one coronal hole is being replaced with another, and that's being replaced with another. Then there's broad consensus, and then there appears to be split consensus until broad consensus appears in the replaced coronal hole. And it has this long tail shape here, which is a very nice aspect of the model. And then you're going to see another jump happening. So let's just watch this for a bit. So I'm going to go back a little bit into discussing about what we do with modeling as footpoint probability distributions. So we talked about different theoretical reasons there's going to be uncertainty in the calculation, and now I'm going to say the specific things that go into the varied dimensions which generate all the statistics that we have. So first of all, parcels are arriving ballistically throughout a wide time window around the target point in the solar system. We know from experience that solar wind models often have the right features, but they come a day late, they come a day too early, sometimes they're stretched. So we want to be generous with our connectivity arriving at the right point at the right time. Also, when we have that ring of sub-satellite points, which we launch partials from on the outer boundary of the model, we perturb those up and down by half a degree in latitude to have some variation in that uncertainty. We use maps from plus or minus 12 hours for the same reason of coming a little too soon or a little too late. And then we have 12 realizations from ADAPT's magnetogram input. And what we hope is that together this has a well-rounded opinion that considers uncertainty from the multiple sources to have a broad opinion on the footpoint probability distribution. In a sense, this can be thought of as like a confidence interval of where it is in a loose sense, where when you have 90% in that region, you have a 90% consensus, 90% confidence that the footpoint comes from that region. You might have noticed that we have smooth probability distributions when what we actually calculate are a number of very discrete footpoint locations. So there's a method that we use for arriving at that smooth probability distribution. So we use a method called kernel density estimation using Gaussian kernels. And essentially what this is that at each point estimate, you place a small Gaussian at each of the points, and then where there's many Gaussians together, they add up to a tall peak, and where there's very few points there, it stays small. And but most importantly, between the points is a smooth transition between high and low. This works to be adaptive to the distribution of the points in the sense that, like what we saw before, you can have a bimodal distribution and you can have a tailed distribution, which is much more advantageous than if we were to fit a Gaussian to all of the points together and then force a Gaussian structure on the distribution of points. This is much more adaptive. I want to briefly touch on our ongoing work with validation of this model. It's difficult to validate because there is no ground truth data set for where the solar wind is coming from. But while we can't do a direct comparison in that sense, we can compare characteristics of what the model distribution predicts with the data observed with the spacecraft. So taking spacecraft in situ data at ACE, for example, the model during a coronal hole transition from positive to negative polarity, you're going to see BR move from positive to negative in the satellite. How does that compare with how the distribution of BR from the foot-point probability distribution, how does that compare with the satellite data? And similarly, how does the solar wind velocity, distribution of solar wind velocities, compare to what's observed at ACE? Are we at most points, at most times, near the expected value? How often are we not? There are probabilistic validation methods that go back for decades within meteorology for considering these kinds of topics. So this concludes my talk. I wanted to end off by saying we expect this to be public around winter time at the CCMC for both real-time ongoing predictions and also runs on request for historical events. You'll be able to see the plots that we showed here and also download the probability fields and the identification of individual regions with expected values per region, most probable point per region, and so forth. So those can be plugged directly into research analysis. We welcome all feedback and suggestions. And if you would like me to do a run before the winter that would be useful for your study, you can find my email there too for that. Thank you very much.